All right, so let's take a look at something called the nuclear binding energy. So think back to Chem 101. You learned about the law of conservation of mass, and then you learned another one for energy. And so independently, they say, you know, we can't create or destroy matter, and then we can't create or destroy energy, right? We can only transfer these things. And so independently, that actually is kind of not totally true, because we can convert one thing to the other. So remember, Einstein told us that energy is equal to mass times the speed of light squared. So this is energy, obviously in joules. And then if you break it down to SI units, it's kilograms meters squared over seconds squared. This is mass in kilograms. It's the SI unit for mass. And then this is speed of light. And it's equal to 3.00 times 10 to the 8 meters per second. And then it gets squared, so you see all the units work out. And so basically what Einstein told us is that we can convert mass and energy. So it's not necessarily that all the mass in the universe is constant or all the energy is constant, but that the sum of the two is constant. So we can convert mass to energy or energy to mass. And so let's take a look at an example of that. So the formation of a nucleus is exothermic. So it releases energy. And when we're doing this, we're taking mass and converting it to energy. So let's take a look at helium-4 again. So here we have 2 protons, 2 neutrons, and 2 electrons for helium, right? Neutral helium-4. And so if you were to take the masses of this and add them up, so we have 2 times the mass of a proton, which is 1.0073 atomic mass units. That's a proton. Add that up to 2 neutrons, so they each weigh 1.0087 AMU. That's your neutron. And then add that up to the mass of 2 electrons, which is 2 times 0.00055 AMU. That's your electrons. If you were to sum that up, you get 4.0331 AMU. And that's how much you would predict a helium atom weighs. And it makes sense, right? A helium is 2 protons, 2 neutrons, 2 electrons. So it should weigh as much as 2 protons, 2 neutrons, and 2 electrons, right? So we have predicted here. .0331 AMU. And then if we take a look at the actual mass, right, take an actual atom and weigh it, we get 4.0026 AMU. And so you can tell it's actually not the same. And if we take a look at the change in the mass, right, we can see our real mass is lighter than our predicted mass. So there's a kind of 0.0305 AMU that aren't accounted for. And so naturally the question is, where did this mass go? And the answer is it's converted to energy and released. And so you can take this mass, you could plug it in to your E equals mc squared and figure out how much energy is released when this reaction occurs. So can we think of any place where this reaction occurs commonly? And the answer is yes. So this reaction is kind of always occurring in our sun, right? So you can see in this little picture here, the sun is a gigantic ball of hydrogen. It's basically a gigantic nuclear furnace where hydrogens combine to form helium. And when that happens, there's a whole bunch of energy released that we see as sunlight. So take a look in your book for a kind of walkthrough through one of these problems. It's basically kind of plugging and chugging, just making sure your units are all right. So it's in chapter exercise 21.2 on your own. And you're going to be calculating this nuclear binding energy.